Kia ora and welcome to what is the last video in the 2012 exam run through. Question 5 here consists of 3 parts. The first part is actually very similar to one we did in question 4. We've got a multivariable equation that's represented as a graph. We need to then connect the lines, the knowledge of the slopes of those lines to a hyperbola. And then part B is a very tricky question. It's involving a proof to do with midpoints and parallel lines. This question was set, or 2012 was a paper set when conics was an external assessment, and so students would have been a lot more familiar with some of the conics work. There used to be 4 externals, the 3 that are currently, plus conics was a shorter one. Okay, so the first question here, show that the lines can be represented by the following equation. So there are 6 lines. And if we think about the brackets there, each of them generate 2 of them. The first one's pretty straightforward. X squared minus y squared is y equals plus or minus x. And we're told that the lines are separated by equal angles. So if we can see this line that comes through, actually we'll keep the colours consistent. There we go, yellow going through there and through there, has a slope of pi over 4. And there we go, tan of pi over 4 is equal to 1. What you need to realise here is that tan of theta is equal to opposite over adjacent. So if we've got a line that comes through here at an angle of theta, opposite over adjacent is rise over run. So tan theta is equal to m, the gradient of the line. Okay, the second bracket isn't as easy as to what lines these actually represent. So we need to solve that equal to 0. X squared equals 7 minus 4 root 3 y squared. We want to make y the subject of this line, so we need to divide both sides by 7 minus 4 root 3. The numbers have been chosen because of their properties. Something nice happens when we work out what 1 over 7 minus 4 root 3 is. We times by the conjugate. 7 plus 4 root 3, top and bottom. And that gives us some double brackets there. 7 plus 4 root 3 times 7 minus 4 root 3 is 7 squared, 49, minus 4 root 3 times 4 root 3, which is 16 times 3, 48. So the denominator there actually equals 1. That's why those numbers have been chosen, even if they seem a bit random to begin with. So you end up getting y squared equals 7 plus 4 root 3 x squared, or y equals plus or minus 7 plus 4 root 3 times x. Again, not so obvious as to where those numbers have come from. So let's do it in a slightly different manner. Let's consider this line here. Let's call it L1. Now, what would the slope of that line be? It's halfway between the x-axis and pi over 4. So it's pi over, or is it? No, it's not halfway at all. The angles are all split evenly around the origin. We take 2 pi, divide it by 12. 2 pi over 12 is going to be equal to one of the gaps. And the gap between lines, 2 pi over 12, pi over 6, right? And then that means that the angle here is pi over 12. First theta for L1 equals pi over 12. So the slope of it is tan of pi over 12. So the equation will be y equals tan of pi over 12 times x, and we're given that one. Tan of pi over 12 is 2 minus root 3. 2 minus root 3 times x. And that's, remember that's y. Here is my stuff up as before. I did not square root that. Hence why it looked a bit strange. Like, how do we know what the square root of 7 plus 4 root 3 is? Well, turns out that is 2 root 3, 1 plus 2 root 3 all squared, I think. So if we go, does that work? No, that's far too big. It's the other way around. It's 2 plus root 3 all squared. If we expand that out, we get 2 squared is 4, root 3 squared is 3, 4 plus 3 is 7, and then we get 2 lots of 2 times root 3. Brilliant. And 2 plus root 3 is a positive number, so when we square root the square, we don't need absolute value symbols. It's plus or minus 2 plus root 3 times x. And I imagine that's probably the other equations. Let's draw these equations here in a different colour. Let's go blue through here. So that one had a slope of pi over 12, and if we haven't solved this bracket equal to 0 yet, so if we do that, x squared equals 7 plus 4 root 3 y squared. Do the same thing with the dropping that down there. Actually, I don't think we need to do that because we now know it's got a square root form, but it's times by conjugate, top and bottom. Okay, the bottom's going to come out to be 1 again, and the top is 7 minus 4 root 3 times x squared, or y is equal to plus or minus the square root. Remember the square root this time, makes it a little bit easier. And the square root of 7 minus 4 root 3, you can get your calculator to do it, but it's another one of those perfect square formats. It's 2 minus root 3 all squared. 2 minus root 3 is also positive, so we don't need to worry about absolute value symbols. 2 minus root 3 all times x. So, okay, so that generates that blue one, that there, 2 minus root 3x is the first one, line 1, because we've just got that. And if I square both sides of that, I'll get the other blue one. Where's 2 minus root 3, there's pi over 12, and 2 plus root 3 is 5 pi over 12, which is this one. And then the green ones, where did I do for the green ones? It was 2 plus, yeah, 2 plus root 3. No, oh gosh. Why did I think that 90 degrees was about 180 degrees? Let's sort of stuff that one up. So 2 plus root 3, 5 pi over 12 is just a little bit less than pi over, it's 6 pi over 12, which is 90 degrees, so that's that one there. And then the other one that will come from that is this one, because it's the plus or minus. And yeah, because we've got a plus or minus, we've got a line that's got a positive slope and a line that's got the same slope, just negative. Okay, I think I've managed to do that all now. Gosh, a bit dodgy for this question. Now we've got to find an equation for a hyperbola that doesn't cross any of the 6 lines. So now that we know which line is which, we can just set 2 of them to be asymptotes. So if I use L1, for example, use L1 as an asymptote. Okay, if we draw a hyperbola where the asymptote is L1 and the other asymptote's minus L1, or L1 reflected in the x-axis. We want a hyperbola that's stuck between them. What you need to know here is that the slope of asymptotes is plus or minus b over a. And the equation of a hyperbola that opens outwards in the right and left direction as an equation of x squared over a squared minus y squared over b squared equals 1, where this dude here is a. You can find that out by setting y is equal to 0, and then you get x is plus or minus a. So your hyperbola also reflects over here. Okay, so if we just set a to equal 1 and b to equal 2 minus root 3, then our slope will be 2 minus root 3 over 1. So x squared over 1 minus y squared over 2 minus root 3 all squared equals 1. That hyperbola there will be stuck between those lines. Okay, now for the last part. In the examiner's report for this exam, it said that this was the trickiest problem, and I imagine looking at the top scholar script that it determined whether the person was top scholar or not. To be honest, the first way I've thought about this question is if we were to draw parallel chords that were vertical or horizontal. So I figured, like, if I draw my ellipse, kind of improved over this exam from Stewie Griffin's head, and if I draw these chords like this way, then based on the symmetry, the midpoints of these chords are all going to lie on the x-axis, which is a straight line. And then my argument was that if I just rotate, these lines, then the midpoints will all rotate by the same angle, and therefore it would still be a line. And I don't know whether they accepted that as an argument, just a pure rotation-based argument, but it's definitely an easy way of explaining how to solve the problem. Okay, stepping you through what the solution looks like in the answers. The first thing is they consider a chord that just has a straight line equation, y equals mx plus c. And then if we want to find out where that chord meets the ellipse, we just need to solve a simultaneous equation and use the ellipse equation given and sub one into the other. So if I sub the chord into the ellipse, I get that equation. Now we're trying to find the points of intersection, so we're trying to find the x values. That there is a quadratic equation if I write it as in its standard format. So the x squared term that comes out of the brackets is m squared, x squared. So that goes together with the x squared over a squared in the first term. My linear term comes out of the brackets as well. Mx times c times 2mc all over b squared times x, and my constant term comes out of the brackets, c squared over b squared, and then minus 1 equals 0. Now I said I needed to find the points of intersection. Actually, I just need to find the midpoint of these intersection points. So the midpoint, which I'll call xm, is equal to the average of the average of the intersection points. And that is a familiar expression. It's the sum of roots. So if I just look at that quadratic equation and work out what the sum of the roots are, the sum of the roots is always minus the term in front of x divided by the term in front of x squared, often written as minus b over a, equals minus b over a. And I'm using inverted commas around that because there's obviously a's and b's in the coefficients already. So if I take the sum of the roots and divide it by 2, I get my midpoint, well, my x value for my midpoint. So it's minus 2mc over b squared all divided by 1 over a squared plus m squared over b squared. To tidy this up a bit, oh, there's also a 2 in there. It's half of that. I'm going to times top and bottom by b squared. That'll get rid of the b squared there, I'll get rid of the b squared there, and it'll get me a b squared on that. And I can also times through by, that's supposed to be a squared. I can times top and bottom by a squared as well. The 2's will cancel too, and I'm left with minus a squared mc, because I'm putting the a squared on top to get rid of it in that bottom fraction, and b squared plus a squared m squared. Now, how do I find my y value for my midpoint? My y value is just, it's on that line, it's on the chord. I haven't proven that it lies on a line here, but I know that it lies on any random chord that I choose. So to find the y value when I've got the x value, I'm just going to plug it into the mx plus c equation. Now, it's not so obvious to know that this is a straight line equation, because it's got a and b from the ellipse equation. It's got the m value, which is the slope of the original chord I chose, but it's also got a plus c thing here. So what they do in the schedule, which is the really clever bit of this equation, is they make c the subject of this equation up here. So let's call this star, we can say from star, we can tell that c equals b squared plus a squared m squared, all times by xm, divided by minus a squared m. And then we can replace the c in this expression, and hopefully that turns into a straight line equation. So ym equals m times minus a squared m times this mess. It's not going to be a mess much longer because the a squared m's are going to cancel. Gosh, what have I got? Oh, that's just putting in the numerator, then divided by b squared plus a squared m squared, and that's all times together, and then we've got a plus c. Okay, so what cancels here? We've got the a squared m there cancelling with the a squared m there, and we've got a b squared plus a squared m squared there cancelling with a b squared plus a squared m squared there. So I've got my y value of my midpoint is m times xm plus b squared over negative a squared m times xm plus, oopsies, not plus, minus xm. Okay, and that is just one giant constant times xm. But I can put it all together. Got m minus a squared m, sorry, no, that's on the denominator, plus b squared over negative a squared m minus 1, all times xm. Oh, there was a sneaky little thing here. M squared with an m. So it's actually, this last term is minus mxm. Great, those cancel. And we're left with the equation of a straight line. And even more so, that's a straight line that goes through the origin, which it should if you think about the picture. The midpoint is on this line, so you can say the midpoint is of the chords xm, ym lie on the line y equals negative b squared over a squared m times x. In the marking schedule they used capital X and capital Y to distinguish from the x and y in the other equation. I don't think that's too important, although I did use xm and ym the whole way through to make sure that I knew the difference between a specific point and a general point. But now I've switched into general points. I'm talking about xm, ym being just a specific point on a general line. And that's the answer to the question. Quite a sneaky question because you needed to write ym in terms of xm. That was the to try and show that it's a linear relationship. But other things that were nice in that is knowing that your sum of the roots formula for a quadratic equation will help you find the midpoint. We didn't need to solve a quadratic, find the x values, then find the average. We just went straight to the coefficients to find the sum of the roots. And knowing that we could just start off with y equals mx plus c, any chord with any slope and any y-intercept. Just if you were thinking that the midpoint of the chord would always lie in a straight line, no matter what the curve, and that maybe an ellipse was just a specific one they used as an example there, I've just made a quick GeoGebra diagram to dispel that. We can see there that A and B are the 2 points where the random chord I've chosen, y equals mx plus c, meets the function y equals e to the x. C is the midpoint, and I've put the trace on the midpoint. So if I slide the curve upwards, keeping the same slope but just changing its y-intercept, it's like, oh, okay, the midpoint is on a straight line. But if you slide it up far enough, you can see it is curving. And if I change that up even more, and just zoom out a little bit, it's even more obvious that we are curving. And I mean, if you want to change the function up and make y equals sine x to have a look at what happens there, you can easily do that. So the symmetry of the ellipse meant that the midpoints of those chords lay on a line. And you could find other functions where that's the case as well, like a parabola y equals x squared will have the midpoints all lying along the y-axis.